Hello, my name is Eric Osborne. I'm a technical manager at Woodard & Curran, which is an environmental engineering firm. I'm located in Portland, Maine, and I'll be giving this Module 1 Introduction to Wastewater Solids Handling. Before I get started, I want to say thank you for the good work you're doing to keep our water clean and to keep people healthy during this crazy, unusual time. And I also want to say thank you for being willing to try out this new remote learning format. So let's get started. The agenda for Module 1 is, first we're going to talk about why solids are important. We're going to talk about their sources and characteristics. We're going to talk about solids processing systems in general, and one specific part of the solids processing system, solids thickening. So why are solids important? Wastewater treatment creates two things, clean water and solids, otherwise known as biosolids, residuals, or sludge. I may end up calling this all three of these things today. So these are all terms that mean the same thing. As long as wastewater is flowing to your plant, you're making solids, and you have to remove what you make. Disposal of solids can be a major part of your annual operating expenses. And processing solids can be very O&M intensive and can be a big portion of how operators at your plant spend their time. Solids are also important because they can cause potential issues such as odors. If allowed to accumulate in the liquid process too much, they can cause process upsets. And if the solids processing system isn't working well, you can recycle solids and dissolved material back to the liquid process. Because of these issues, solids can be the tail that wags the dog at your plant. Problems with your solids handling can cause problems on the liquid treatment side and even lead to permit violations. In addition to being a potential source of issues, solids handling also presents an opportunity. It's one of the places where operators can make the most impact. Improvements to the solids handling process can simplify operations, save money, and even improve the liquid process. And for operators who are feeling particularly creative and entrepreneurial, there are additional opportunities. Biosolids can be used as a fuel. It can be turned into a gas or pellets and burned. Solids can be digested to make heat and electricity. And solids can also be used as fertilizer and organic material for soil restoration. Where do solids come from? Even though these things here look like UFOs, solids do not come from outer space. These are actually primary clarifiers, which is one possible source for solids. Most plants also have secondary clarifiers, which is another source for solids. Solids can also come from your tertiary process if you have one. These solids can be metal salts that were added for pee removal, or solids produced from effluent filters. And septage and hauled wastes can also be sources of solids. The characteristics of solids depend on where they've come from. If your plant has primary clarifiers, the primary solids are typically 1 to 6% solids. They are the organic and inorganic material that's not removed by the headworks. It's relatively heavy, gritty, and potentially high BOD, and also contains fibrous material. The secondary solids, on the other hand, are less dense. They're only about 0.5 to 1.5% solids. Secondary solids are the microorganisms grown in secondary treatment to remove BOD. They're cleaner, less odorous than primary solids. As I mentioned, they're lower density. They also tend to be biologically active, especially for plants with low SRTs. Tertiary solids, if your plant has it, are very variable. As I mentioned before, these consist of metal salts. They can also be backwashed from effluent filters. Tertiary solids are typically poor settling and difficult to thicken and dewater. Septage is typically 1.5%. Septage received from residential sources is usually cleaner than commercial, but use caution because depending on where your septage is coming from, it can contain rocks and other debris. The characteristics of your sludge may be different than someone else's. It really depends on your particular plant configuration. This table shows how the solids concentration of different sludges varies depending on the specific processes used at a plant. For example, in Lowell, Massachusetts, at the Lowell Regional Wastewater Utility, they send their primary sludge to a cyclone degritter. In order for this to work, they have to pump at a high rate, so their primary sludge is relatively thin. By contrast, at smaller plants that don't have primary clarifiers, the material that would have ended up in the primary sludge ends up in the secondary sludge. So the secondary sludge is relatively dense, and this is the case for a lot of small plants in Maine, including the plant at Madawaska, that don't have primary clarifiers. Different types of secondary processes also produce different secondary sludges. At Greater Augusta Utility District, for example, they use a high purity oxygen process. And then sludges can be different too, depending on the point in the solids handling process. For example, at the Lewis and Auburn plant, they have gravity thickeners, and the primary sludge is different going into the gravity thickener than it is coming out. A few final points on characteristics to watch out for. Sludge, particularly primary sludge in a plant that doesn't have grit removal, or secondary sludge in a plant that doesn't have grit removal or primaries, can contain a lot of grit. That's what this picture shows, grit that was in primary sludge at a large plant with a old collection system and failing sewers. So a lot of that material ends up in the sewers and comes out in the primary sludge. And this grit is so large, it's almost gravel-like. Sludge can also contain grease, oil, scum. Polymer is used at different points in the sludge handling process to condition the sludge, and this can really change its characteristics. And if you're in a plant that's trying to remove phosphorus, you remove phosphorus in your sludge. So some sludges can contain a fairly high amount of phosphorus. And if phosphorus is part of your permit, you want to handle your sludge in such a way that you don't re-release the phosphorus. This is an overview of what a solids handling system at a large plant might look like. And as I talk through this, I'm also going to talk about how smaller plants or even just different plants can be different. There's many variations on a solids handling system. Of course, it all starts with the source of the solids, either primary, secondary, or other solids, hauled waste or septage. Primary solids often undergo some kind of preliminary treatment to take out that grit. You can have grinders or screens. Secondary solids is often stored first, usually in some kind of aerated storage tank. And then the first process that's applied to these is thickening. The goal of thickening is to remove water and increase your solids concentration to about 6%. By doing this, you greatly reduce the amount of the volume of the sludge that you're trying to process. So you can reduce the size of downstream equipment and reduce the amount of hauling that you've got to do. Some plants have separate thickening for their primary and secondary sludges. In some plants, the secondary sludge is blended with the primary and they're thickened together. In small plants, thickening might be as far as your sludge handling system goes. At that point, you pump it onto a truck and it's sent off to ultimate disposal. Some plants have additional steps, such as dewatering. The goal of dewatering is to remove even more water and concentrate your sludge up to 20 to 30% solids, reducing its volume even more. Some plants may also have a step like digestion. The purpose of digestion is to reduce your volatile solids. It converts roughly half of them into biogas. There's other processes out there too, such as sludge gasification. Some plants also have lime addition to their sludge to condition it. Ultimately, the sludge is hauled off site and for disposal as compost. Sometimes it's land applied, incinerated, or landfilled. One final point, don't show pumps on this diagram just for simplicity, but pumping is a really important part of sludge handling that'll be talked about in a later module. Piping is also important, as is polymer addition and odor control. Just briefly, I mentioned preliminary treatment on the previous slide as often the first process for handling primary sludge, and basically taking out the debris, the grit, the stringy material that can be in that sludge. The most common preliminary treatment step is grinding. This picture here is the kind of grinder that you might see on primary sludge piping. Some plants that don't have grit removal on their forward flow, particularly larger plants, the grit will end up in the primary sludge, so they actually have grit removal system on the primary sludge. The benefit of this is the grit removal system can be smaller and the grit is more concentrated at this point. Another preliminary treatment step, which isn't very common but does exist, is screening. This picture here shows inline screening of primary sludge. I'm going to spend a little bit of time talking about thickening. This is a fairly important step. Most plants that handle sludge at least have thickening. The goal of thickening, again, is to remove water to reduce the volume of sludge. For example, if your sludge is 2% and you can thicken it to 6%, you've reduced its volume by 3 times. That means that you can truck only a third as much as you'd have to if you didn't thicken it. Thickening makes the sludge easier to store, haul, and process. There are a number of common technologies used for thickening: gravity thickeners, rotary drum thickeners, gravity belt thickeners, dissolved air flotation thickeners, and centrifuges. And I'll talk a little bit more about each of those now. Gravity thickening is perhaps the simplest process. Sludge is introduced into the center of a large tank, such as this, and it's just given time to settle out. The sludge concentrates on the bottom and clean water flows off the top. One thing to note is the slowly rotating sludge collection mechanism, which pushes sludge toward the center. It also has these tines or rakes, and the purpose of this is to carve grooves in the mat of sludge to give the water a place to escape upward as the sludge settles downward. Rotary drum thickening is another very common type of sludge thickening. It's also referred to as rotary screen or rotary sludge thickening. So you'll see RST as well. RST, RDT, all these terms mean exactly the same thing. Rotary drum thickening is common in smaller plants, especially plants that just have a single sludge. Like other forms of mechanical thickening, the first step in rotary drum thickening is to add polymer and flocculate the sludge. So the purpose of this tank is to give, it has a mixer on top, which provides gentle mixing and just provides time for the sludge to form flock that then thickens better. And the sludge flows by gravity into this unit, which happens to be inclined. Some rotary drum thickeners are parallel to the floor, but they all look more or less like this on the inside. There are these flights which convey the sludge through the drum, and I think in this case it comes in the back and falls out the front here. In addition to conveying the sludge, these flights also gently stir the sludge and slice it, giving the water a chance to escape. And the water drains out through the drum, which is covered with a fine mesh screen. Rotary drum thickening is a fairly low speed, relatively simple to operate process. Gravity belt thickening is similar in that it's another low speed, fairly easy to operate process. It's not as easy to enclose as a drum thickener. These gravity belt thickeners can be a little bit messier and a little bit more odorous. The way these work is that the sludge is dumped on one end of the belt. These typically don't have a separate flocculation tank because the belt has a zone up front to allow flocculation to occur. The belt moves along slowly, and the belt is made out of a perforated mesh, so water drains through and the sludge is conveyed across the top. This close-up here shows what the top of the unit looks like, and they're these cylinders, or sometimes they're more triangle-shaped, to agitate the sludge, stir it, and again provide channels for the water to escape. Dissolved air flotation thickening is another type of thickening. It's a little less common in municipal plants. It's used for sludges that tend to want to float anyway. These could be things like secondary sludge that's kind of neutrally buoyant, or secondary sludge mixed with scum that does tend to float. It's also common in industrial processes, especially food processing, where there may be a lot of grease involved. And the way this works is there's a recirculation pump, which recirculates liquid in the tank. It's a high pressure pump that pressurizes the liquid, and air is injected into that pressurized liquid. It's then introduced to the influent end of the gravity thickener. The pressure is released and it's mixed with the sludge. And what happens when that pressure is released is exactly like pouring a glass of soda. The air that's pressurized in there comes out in the form of tiny bubbles which rise to the top, and they take the sludge with it. And this photo here shows how the sludge rises to the top and is skimmed off. These are complicated, mechanically intensive processes, and that's probably the reason why they're not common. If you see them at all, it's in larger plants typically. This table provides a summary of what I just talked about. Gravity thickener is the first one we showed. These are mostly used for primary sludge because primary sludge is heavier and settles well by gravity. They have a large footprint. That's probably their largest disadvantage. So installing them is fairly expensive and takes some space, but they're extremely simple to operate. They are sometimes used on a blend of primary and secondary sludge, but in this case they should be used with caution because the primary sludge contains a lot of BOD and the secondary sludge contains active microorganisms. And when you mix those two things together, you get a lot of biological activity, which can lead to odors and basically can digest the sludge and release organic material back into your liquid stream, causing upsets. Rotary drum thickeners are commonly used on secondary sludge or in plants with no primaries. Then secondary sludge is essentially a blend of primary and secondary. As I mentioned, they require flocculation in polymer. They're common in small plants with a single sludge. It's a simple process that's easily enclosed. Belt thickeners are similar in that they're typically used on secondary sludge or a blend. They're a mechanical process, so they require flocculation in polymer as well. They can be a little messier. Dissolved air thickening is used on secondary sludges, also on a blend of secondary and scum. It's good for materials that tend to float anyway and contain scum and grease. They're large and complex and not really common in a municipal setting. And finally, centrifuges, which I didn't show a picture of. This is another type of thickening that's used on secondary sludge typically. The advantage of centrifuges is they're flexible. They can also be used for dewatering sludge. They take up very little space, but they're relatively high energy. They're a little less common for thickening than some of the other methods. The last slide of Module 1 that I want to go through is blending. In some plants that have multiple sludges, there's points in the process where the sludge needs to be blended. This is important ahead of thickening or dewatering to have a consistent sludge so that those processes run well. The best way to do blending is in a blend tank. If you have the luxury of that at your plant, you send the two sludges to the blend tank, they're mixed with a mechanical mixer, and the blended sludge is pumped to thickening or dewatering. Inline blending also works well. This is when the two sludges are just blended together with a pipe. Often a mixing valve is added to promote turbulence and mixing within the pipe. And this is typically how sludge is blended ahead of gravity thickeners. That's the end of Module 1. Thank you for listening.
This begins part 2 of the Introduction to Wastewater Solids Handling. My name is Julianne Page, and I'm an environmental engineer at Woodard & Curran with about 8 years of experience in the design and construction oversight of municipal wastewater treatment facilities and collection systems. During this section, I'll give an overview of sludge dewatering systems, including the various types of technologies that are commonly used for dewatering. I'll also introduce the topic of the economic benefits of implementing dewatering, which will be further expanded upon during a subsequent video. Finally, I'll discuss sludge conditioning in the form of polymer feed systems. Our first topic for this section is a discussion of sludge dewatering. The goal of both sludge thickening and sludge dewatering is to remove water from the sludge, because the more water you remove, the less weight you have to dispose of. The main difference between thickening and dewatering is that dewatering technologies remove more water than thickening technologies. What the various dewatering technologies have in common is illustrated by this figure. A mixture of polymer and sludge enters the piece of equipment. What comes out is the dewatered sludge cake, which is then disposed of, and filtrate, which is essentially the water removed from the sludge cake and which is typically returned into the facility for treatment. There are many different types of dewatering technologies, but our discussion today will focus on the 4 that are most commonly used: screw presses, rotary presses, centrifuges, and belt filter presses. The first technology we'll go over is the screw press. This equipment is typically comprised of a screw that slowly rotates within a stationary screen basket. As the screw rotates, sludge travels along the screw and is pressed against the screen. Water passes through the screen and exits the bottom of the screw press as filtrate. The dewatered sludge is discharged from a chute at the end of the screw. Screw presses are enclosed within a solid housing to contain odors and splashing that may occur from the spray bar that's aimed at the screen. This slide shows an example of 2 manufacturers that utilize this principle. This next slide shows an example of a manufacturer that has slightly modified the traditional screw press method. Instead of pressing the screw against a screen basket, PW Tech uses a series of rings around the screw that alternate between fixed rings and rings that are allowed to move up and down as the screw flights rotate. The next technology is a rotary press, which consists of a modular series of filtration units. Each unit is composed of two parallel screen plates that rotate at a low speed. Sludge is fed into the space between the two plates. So as the plates rotate, water is pressed out through the screens and the dewatered sludge is transported to the outlet. The sludge processing capacity of the rotary press can be increased by adding more filtration units. Similar to the screw press, each filtration unit is enclosed within a solid housing to contain odors and spray water. The centrifuge might look similar to the photos of the screw press we just discussed, but the only real similarity is that they both utilize screws. In a centrifuge, the rotating screw is enclosed within a solid bowl that rotates at a very high speed. This causes the sludge to separate out into a dense sludge cake and water. These units are also enclosed within a solid housing to capture odors and spray water. Belt filter presses are a bit of a different animal. In this process, sludge is fed onto a porous belt where it's thickened slightly in what's called the gravity drainage zone. Pressure is then applied to the sludge from above by a second belt in the low pressure or wedge zone. Then in the high pressure zone, the top and bottom belts are actually passed around a series of rollers that squeeze additional water out of the sludge before the cake is discharged. As you can see in these figures, belt filter presses can come in either a horizontal or a vertical configuration. And the capacity of these units can be increased by just increasing the length of the belt system. Unlike any of the previous three technologies, these units are not enclosed within a housing and are often installed within a dedicated room to contain odors and spray water. So before we move on from sludge dewatering technologies, I wanted to share this table that provides a brief summary of the general advantages and disadvantages of each. So as we touched on earlier, the screw press, rotary press, and centrifuge are all enclosed, which provides the advantage of minimizing odors and splashing from the spray water systems. On the other hand, the belt filter press is not enclosed, which can really create a messy working environment if a separate room or some kind of containment area is not included in the design. In terms of electric requirement, the screw press, rotary press, and belt filter press all operate at relatively low speeds and therefore require smaller motors. But the high-speed operation and multiple motors of the centrifuge result in a higher power requirement. The centrifuge also tends to require a higher polymer dose than the other technologies, which then results in a higher overall operating cost when combined with the electrical requirements. However, both the centrifuge and belt press can provide a high sludge throughput per unit area footprint than the other two, and both of these are capable of dewatering waste-activated sludge on its own, whereas the screw press and rotary press tend to perform poorly unless the sludge feed consists of both of a blend of both primary and waste-activated sludge. As you can see, there's really no one technology that will be the answer to every facility's dewatering needs. As a conclusion to our sludge dewatering technologies discussion, I've just included this example chart that was developed as part of an evaluation of whether or not to replace existing belt filter presses with another technology. This table presents a comparison of the operating costs associated with each of the options, including polymer use, energy cost, and the dewatered cake disposal costs. In this example, all three of the other technologies would require a higher polymer dose than the existing belt filter presses, but all three of them would also result in a significantly lower sludge disposal cost because the belt filter press typically doesn't produce as dry of a cake as the others do. The end result of this particular comparison is that replacement of the existing belt filter presses with a Huber screw press would actually result in the greatest operational cost savings. We're going to continue with the operational cost discussion and zoom in a little closer on the dewatered cake disposal component. As you can see on this example graph, the dewatered sludge volume in wet tons per day that needs to be disposed of decreases exponentially with the dry solids content of the sludge. Sludge thickening typically results in a cake between 1 and 5% solids, whereas sludge dewatering typically results in a sludge cake between 20 and 40% solids. This means that the sludge volume produced by a dewatering system can be several times lower than that produced by a thickening system alone. As an example, this next figure shows how about 96,000 gallons of sludge thickened to a solids content of 5% equates to 400 wet tons per day that someone then has to haul away and therefore pay to have hauled away. This is approximately 16 25-ton truckloads per day. If this sludge is then dewatered to a solids content of 20%, the result is just 100 wet tons generated per day, or approximately 4 truckloads. By contrast, if that same 400 wet tons of 5% thickened sludge is dewatered to a solids content of 30%, only 67 wet tons is generated per day. So that extra 10% solids content in the dewatered sludge represents a savings of a whole truckload of sludge hauled each day over the previous example. So you can clearly see how the savings will start to accumulate over just the first year of operation of a dewatering system. At this point, we're going to switch gears a little bit and talk about polymer. I've mentioned polymer several times throughout the module as a substance that is added to the sludge prior to it being fed into the dewatering equipment. The word polymer is a general term that refers to long chains of sticky molecules that bind sludge particles together to form a flock. This makes it easier for the dewatering equipment to effectively separate the solid particles from the liquid water. Sludge primarily has a negative charge, so positively charged or cationic polymers are typically used for flocculation. There are many different types of polymer available that are based on parameters such as molecular weight, charge density, and percent active content. The first step in designing a polymer feed system is to select a polymer that will result in the highest percent solids in your dewatered cake sludge. This is typically done by performing a jar test, which allows a side-by-side comparison of how well different polymers form flocks within a mixed sludge sample. The dewatering equipment vendor can also typically perform full-scale lab testing to determine which polymer will work best with their specific equipment. However, even with a recommendation from the lab, it may be necessary during initial startup of the dewatering equipment to try several different types of polymer before the final selection is made. The operator can then vary parameters such as makedown concentration and dose to fine-tune how the polymer feed system is ultimately run. The addition of polymer is necessary for all thickening and dewatering technologies. In general, the thickening and dewatering processes often require two different types of polymer, but it's possible at some facilities to actually use the same polymer for both processes. It is therefore recommended that the dewatering polymer be tested on thickened sludge that has had its own polymer added to it already to accurately reflect field conditions. It's also therefore typically necessary to install two separate polymer storage, makedown, and delivery systems. Design of a polymer feed system begins with the anticipated polymer dose. As I've already mentioned, the exact polymer dose will not be known until the equipment is operational. So this estimated dose is calculated based on the typical range of polymer volume and concentration that depends on the type of dewatering equipment and the type of sludge cake. In reality, the polymer dose will vary based on sludge quality and other impacts such as wet weather and seasonal variation. This figure provides an example of a facility that requires different polymer feed systems for thickening and dewatering. Each system requires its own bulk storage tank, mixing pump, blending unit, aging tank, polymer pumps, and injection system. This last slide shows just a few photos of the polymer system at the Labka facility where this training was originally scheduled to be held. Although polymer is chemically inert and non-corrosive, there are containment curbs around the storage and feed system areas to prevent spills, since polymer is a very slippery compound that can lead to operator slips and falls. This concludes the second part of the Introduction to Wastewater Solids Handling training. Thanks for viewing this presentation, and feel free to ask any questions you might have on the topics covered here during the live question and answer sessions that will be held on April 30th.
Thank you very much, Julianne. Now we're going to start Module 3 of Introduction to Wastewater Solids Handling. My name is Tom Harrer. I'm a project engineer at Woodard & Curran with about 10 years experience in wastewater and water treatment design. So in this module, we'll be talking about sludge storage, pumping, and conveyance. So first, we'll talk about sludge storage and mixing. Next, we'll talk about types of sludge pumps. Next, we'll talk about sludge piping. Then we'll talk about cake conveyance. And lastly, we'll touch on overview of cake stabilization. The first topic is sludge storage. So the first thing to mention is sludge storage in the clarifiers, either primary or secondary, is not desired and is typically only used in emergency circumstances. So for that reason, storage of liquid sludge is usually an aspect of the sludge handling design. So one way of dealing with this is storing sludge in gravity thickeners. This is generally good, in smaller scale facilities, and they can get away with just storing all the sludge in a gravity thickener. But as the facility size grows, there's more of a need to store the sludge in an alternate location. So the preferred way is storing thickened sludge, and the reason for this is it takes up less space, so you can build less tank volume. But one consideration with this, it's generally not a good idea to mix primary sludge and waste activated sludge. You can store dewatered sludge, but this is not common. It does take up the least amount of space, but it does have issues with handling. Therefore, it's not commonly seen. And the last consideration, this is just an overall consideration for any storage system, is incorporating mixing, aeration, and odor control. All right, so touching on mixing for sludge storage tanks or blend tanks, it's a good reason to mix your sludge. The reasons for that, one, if you're blending your sludge sources together, it helps to create a more homogenized sludge mixture. In general, if you're blending or not blending your sludges, mixing helps reduce or eliminate the stratification or the separation of your sludge. Also, it allows the grit particles or your inorganic particles to stay suspended without settling out to the bottom of the tank. And lastly, mixing the sludge helps reduce the septicity or the stagnation of the sludge, which can lead to things like odor issues as well as issues with your thickening process. All right, so there's a bunch of different types of mixers. So the most common are mechanical mixers. So you can see the photo to the right. That's just an example of a common mechanical mixer in a top-mounted orientation. So you can see a motor with a gearbox box up top with a shaft kind of extending into the tank with the impeller that would mix the sludge up. You can also get this in a side-mounted orientation where it kind of go through the sidewall of the tank. Also, with mechanical mixers, there's this type called the hyperboloid, which you can see over in the photo on the far right, the shafted mixer with the kind of the white circular blade at the bottom. One of the leading manufacturers is this company, Invent. They're pretty popular mixer. You see a lot of plants. Another way of mixing is to pump the sludge. So with this, you would draw directly from the tank and then pump it right back into the tank through these flow nozzles that shoots the sludge out at a high velocity. So this creates this, mixing nature by pumping the sludge around and shooting it around at high velocities. Another way of mixing it is with draft tubes with either recirculated gases or through mechanical means. Another type of mixer is a submersible mixer, which you can see on the bottom right, that green mixer. So this mixer would actually be submerged fully in the tank. And then lastly is diffused air. So you can see the photo kind of down at the bottom. This is, you just pump air into your tanks through a diffuser system, either a coarse bubble or fine bubble diffuser, to mix up your sludge. So on this slide, you can see the photo on the left. That's another example of a hyperboloid mixer. And then the photo on the right kind of shows a Rotomix system, which is a type of sludge pumping mix system. So here's a quick example of cake storage. So here the cake would be conveyed up into these hoppers that are just sitting right above the dumpsters. So the cake would just sit in there and just get loaded in the dumpsters and conveyed offsite. All right, next we're gonna talk about sludge pumping. So there's a bunch of different types of pumps that can be utilized for sludge pumping. On the screen here, we have a couple examples. On the left, you have double disc pumps. So both the top and bottom photo on the left depict a double disc pump. One of the common manufacturers is Penn Valley. So sometimes you hear Penn Valley pumps and double disc pumps kind of used synonymously. The photo in the middle is a rotary lobe pump. So there's these lobes that actually move the fluid around. The photos on the right depict two different types of centrifugal pumps. One's a chopper pump. The one on the top, this has like a cutter blade that will cut up any material that's in the fluid. So say there's a bunch of rags or something in the sludge. The chopper pump does a good job of chopping up the rag to allow it to be pumped and not clog up the impeller. The one on the bottom is a recessed or vortex impeller pump. So the impeller actually sits recessed outside of the volute. This allows big chunks of solids or big solid material to pass freely through the pump without getting bound up on the impeller. So a couple more examples of sludge pumps. On the top left, we have a parasaltic or a hose pump. The photo on the bottom details a progressive cavity pump. The photo on the top right shows a piston pump, and the one on the bottom right shows a diaphragm pump. So all the different styles of pumps all have their pluses and minuses to them. But one thing definitely to consider is the suction lift capacities, because certain pumps have more limitations on your suction lift capabilities. So just in selecting the pump, that's just an important consideration. Another one is providing overpressure protection for positive displacement style pumps. So these are the pumps you can kind of see on the below table: the rotary lobe, progressive cavity, double disc, parasaltic, diaphragm, piston pumps. All these are positive displacement style pumps, and they will just pump and pump and pump. So one big issue with sludge is you can get clogs in your piping. So if your pipeline gets all clogged up, the PD pumps are just gonna pump and blow your piping apart. So it's important to kind of design in some overprotection to shut off the pump if the discharge pressure gets too high. So looking at this table here, this kind of details what pump is best for different types of applications. So you can kind of see, the green is good, yellow's okay, and red's not recommended. So, depending on what type of sludge you're pumping, there's different pluses and minuses for choosing different types of pumps. So looking more into your pump selection, a couple important characteristics are what percent solids you're actually pumping and kind of your discharge conditions of your pumps. So depending on, what you're actually pumping, there's certain limitations to your type of pump uh, that you want to select. So for example, if you're pumping, really dry sludge cake, you want to select something like a progressive cavity pump because it can pump up. It can pump up to about 25% solids. Next thing I want to touch on is just some special considerations for sludge piping and also pump selection. So the important thing to realize and take away from this is that sludge doesn't act like water. The sludge TDH or total discharge head can be many times that of water. Water is a Newtonian fluid, meaning that the head loss or pressure drop is proportional to the velocity or viscosity of the fluid. Sludge doesn't act like that. It can be exponential to that. So, there's two methods for estimating kind of the head loss or pressure drop with sludge, and that's using a multiplier from the chart you can kind of see over to the right, and also a friction factor based off mechanical properties. So just taking a closer look at the graph over to the right, you can kind of see that the graph represents different percent solids, and then on the x-axis it shows the velocity, and then on the y-axis it shows the multiplication factor. So if we take something like 12% solids, you can kind of see that's that really steep portion on the graph there. At something like 1.5 to 2 feet per second velocity, the multiplication factor would be about 70 times that of water. So you're getting a lot more head loss pumping sludge than you are pumping water. Some other considerations to take into account is, grits and rags and other materials that are going to be in your sludge that can clog up and gum up your piping and your pumps, and also grease and scum that may coat inside of the pipes. All right, so we're going to talk about some considerations for your piping. So, important thing with your sludge piping is having an ability to clean it out. So there's a bunch of different ways you can, clean out your piping. One thing is just adding a flushing connection. So this is just, putting a location in the piping where you can hook up a water line, either plant water or city water, just flush the line out. So adding a lot of those flushing connections, make sure the connection's actually big enough so you can actually push a lot of water through it, and make sure the flushing valves are accessible so you can actually get to them, push it through. Another way to clean out your lines is adding pigging stations. So this is where you're going to actually pass, something solid through the pipe to push things out. Another way is just adding putting clean outs in there so you can physically clean out portions of the line. And another way is add a pump to just pump out the line. So this is the reason why you gotta add those means of cleaning the lines. You can see these pictures of pipes just absolutely clogged up. So you want to figure out some way of avoiding this at all costs and making sure you're maintaining your lines to make sure they do not look like this. So here's just an example of a pigging station that was provided in Plainville, Connecticut. This was installed in a line to deal with a system that was pumping a trickling filter and primary sludge blend that was coating the inside of the pipe. So you can see over here on the photo on the right, kind of shows the pigging station. And here is the receiving station, so you can see the pig kind of being pulled out of the line. So this, that pig is gonna push everything through the line and clear out, all that gunk that was coating the inside of the pipe. Touching now on some considerations for selection of actual piping. So looking in the material selections, one really good material you can select is ductile iron. So just one thing with this is, considering getting a lined piece of ductile, so that's either with a cement lining, plastic or epoxy lining, or glass lining. Also, PVC is a good option, but note this is only really good for low pressure applications. So the actual connecting of the pipe, you want to have, flanged or groove end ductile iron pipe. And this is so you can actually break the thing apart, in case you actually have any clogging. And, similarly with PVC, you don't want solid welded PVC. You want to add some flanges so you can disassemble it. And then when it gets to actually, installing the piping, you want to make sure you have plenty of hangers just for, dealing with that, the potential of, overpressurization and, just the beastly nature of pumping sludge. And the last thing I just want to highlight is, it's recommended that you have a minimum diameter of 6 inches for any sludge pipe. So on this slide here, it just shows a couple examples of, some of the connections. So, the photo on the top left shows ductile iron grooved fitting or Victaulic compression fitting. You can see that elbow over to the right, the silver one. And then you can see some pictures of the PVC with some flanges on there. All right, some further considerations in piping is you're putting the piping system together. One thing is just the design to minimize the amount of bends that you're putting in there. And if you are going to use a bend, try to use a long radius bend when possible. Next is installing your valving. You do not want to put your valves in the vertical position. This is because you can get, the sludge to kind of sit on top of the valve and gum it up. So ideally you want them in the horizontal position. Also kind of tied with your piping is using sanitary wise when possible to provide cleanouts and pig launching and receiving stations. Another consideration is avoiding suction manifolds when possible. And tied with your suction piping is keeping your suction piping as straight as possible. And we know with retrofits, you can't get all these things, so just do the best you can with what you got. Here we got some quick sketches of some pumping and piping arrangements. So on the left is an example of not so good pumping and piping arrangement. So first you can see the suction manifold. There's a single suction pipe for 2 pumps. Next, you see the valves on the discharge end are in the vertical position, and then going over to following along the discharge piping, you can see a T in the vertical position. So the way to improve upon this layout is separating and not having a suction manifold, but having independent suction lines for each pump, installing the valves in a horizontal position, and then putting the T connection in the horizontal position instead of the vertical. And if you can, use a sanitary sweep instead of just a regular T. All right, so touching on some valves, there's a bunch of different valves options that you can get. Some are eccentric plug valves, ball-centric plug valves, ball pull port, pinch valves, knife gates, gate valves, and just also your check valves. So touching right here on just ball-centric plug valves, these are a really good option, but just some considerations, trying to avoid with sludges containing grit, and then also, orientation matters. So, as mentioned before, don't install it in the vertical and in the horizontal position. installing in the correct manner to prevent, solids accumulation. Here's just a quick example of some sludge piping. So this is a pretty good arrangement here. You can see the valves installed in the horizontal position. You got flange piping as well as some compression fittings. Here's another look. This is actually a Lapka here. Another good layout. You have, again, your valves installed in the horizontal position. So next we're going to touch on sludge cake conveyance. So, as I mentioned previously on, talking about the pumps, certain pumps work better for drier sludge cake. So two examples are progressive cavity pumps and as well as high pressure piston pumps, which can pump pretty dry. So moving on from pumping and getting actually to moving the cake around, there's a couple different options. There's shafted conveyors, belt conveyors, as well as shaftless conveyors. So here we just got a picture of Spirec. They're a manufacturer that produces a lot of conveying equipment, particularly shaftless screw conveyors. So here's just a couple pictures of some sludge conveyors. This is a shaftless sludge conveyor at the Haverhill, Massachusetts wastewater plant. Touching here on some advantages and disadvantages of shafted screw conveyors versus shaftless screw conveyors. They're both good options for conveying dry and semi-fluid materials, but the big advantage with the shaftless screw conveyor is, there's no shaft, so, no sludge can stick to the shaft and kind of reduce the conveyor capacity, as well as the bearings are located at the end of the conveyor, which makes maintenance easier. But the big drawback with this is there's kind of, a limit to how big the shaftless conveyor can be. So that's where, the big advantage of the shafted screw conveyor is you can make a much longer conveyor if needed. So in regard to screw conveyors, there's some different orientations that you can install it at. One is an incline screw conveyor. So there's a big advantage with this is when you install the screw in an inclined position, this allows a thin sludge to drain some more, which if you're paying for off-site disposal can provide some cost savings. But some drawbacks with this is that you have reduced capacity with an inclined screw, regardless if it's shafted or shaftless, just due to the orientation, as well as it's going to require more power compared to a horizontal screw the same size. So here's just an example of a conveyor installed in a slight incline. So you can see the discharge location to the conveyor, and then kind of at the bottom you see a drain pipe. Here's another example of an incline conveyor. This one's coupled with a centrifuge, so you can see the centrifuge over to the left is the blue thing with the incline conveyor dumping over to a dumpster on the right. So just one thing to highlight here is this conveyor is provided with an emergency pull cord. This is a good provision to have with conveyors, so you can shut them off in case there's some condition, say someone gets a piece of clothing or their hand or something trapped in the conveyor. You have a way to immediately shut off the piece of machinery right then and there. So here we have an example of an interchange between an incline conveyor and a horizontal conveyor. So depending on the location, you don't always have the luxury of having your sludge processing equipment right adjacent to where you're disposing it. So you do have the options of kind of, jumping from conveyor to get it where you need to go. So getting to the end of the line here, when you're dumping your sludge into your dumpster, there's some considerations to take into account with your conveyor setup in your truck bay or wherever you got your sludge discharging into your dumpsters for hauling off site. So you can see over in the photo on the right, this conveyor is set up with multiple discharge points. This allows the sludge to be evenly dispersed over, the dumpster instead of a single location, which is just going to pile up the sludge, right in one location, which is going to require you to constantly move your sludge can back and forth to get even dispersal of the sludge. So here's a good example of a truck loading bay in Niagara, New York. So you can see that the conveyor setup's got a bunch of points for discharging the sludge into that dumpster. Here we got the truck loading bay over at Lopka. So you can see the photo on the right, you got 2 discharge locations dumping into the dumpster. So we got 2 nice piles of sludge piling up in that dumpster. So you can imagine if there was just one discharge point, you just get this huge amount of sludge. That's just kind of a pain to deal with to fill up your dumpster. So the last topic I want to touch on is sludge cake stabilization. So the reasons for sludge cake stabilization is to reduce pathogens in your sludge cake, eliminate odors, and inhibit or reduce putrefaction of the sludge cake. So some common sludge stabilization methods are addition of lime. So this can either be post or pre-treatment, heat treatment, and anaerobic digestion. So that concludes Module 3 and concludes the Introduction to Wastewater Solids Handling presentation. Thank you all for participating and viewing the presentation. We will have a live Q&A on April 30th. So if you have any questions, feel free to ask it during that time. Thank you very much.